So what's my electronic geometry? Okay, let's see what our possibilities are. Let this be the central atom, and this be areas of high electron density. So now I'm going to show you. The good news in this class is for electronic geometry and molecular geometry, in this class, there is only a total of 6 choices. So anytime you guess at any of these, you got a 1 in 6 chance of getting it right if you don't know anything. Okay, so here we go. But let's show you how you figure it out. Let's say I had a central atom. There were 2 areas of high electron density. And this, you could just use common sense. So what's the furthest they can get apart? See, electron densities try to get as... Remember, electrons don't like each other much. They'll pair up, but after that, that's it. So they try to get as far away from each other. If I have a central atom with 2 areas of high electron density, what's the farthest they can get away from each other? What's the farthest they can get away? And the answer, like the virus, man, you want to get as far away from it as possible, okay? So these things are trying to get as far away from each other as possible, so guess what it makes? A line. So we give this, the name of this, anytime you have 2 lone pairs, the name of the electronic geometry, the name is going to be called linear. So if this were a 2, I would have written linear here, see? Because if I have 2 areas of electron in my mind's eye, I can see that that's got to be linear. Okay, how about 3? What if I have 3? What's the farthest they can get away from each other? The farthest they can get away from each other is 120 degrees apart. That's it. That's as far as they can get. And it makes this triangle shape, but it's flat. So this is called Trigonal Planar. So what I would write here on my answer sheet, and now I would have to write really small. Or if I was really clever and couldn't do that, I would just type trig planar. Got it? Okay, see? And the instructions will tell you, I want a number and only a number here. And don't be drawing me anything. It says give the name. The instructions say write the name. Don't be drawing that picture there. Don't be drawing that. If I ask you to draw it, then you draw that. But right now it's trig planar. Yes? Okay. So let's see what your possibilities are. You can have 2 things connected to the central atom, or you can have 2 areas of high electrons. You can have 3, or you can have 4. Now, just so you know, you can go up to 6, but in this class, I limit it to molecules with no more than 4 groups hanging off of the central atom. Okay, so if you see something with 5 or 6, you can ignore it. I won't ask you that on a test. But really, you can go up to 6. All right? So in other words, everything I ask you, the number of areas of high electron density is either going to be the number 2, 3, or 4. Okay? So if it's 2, it's linear. If it's 3, it's trigonal planar. Well, how about if this had to have been a 4? What would it be? Well, what's the furthest thing 4 things can get away from each other? Now, you might think it's like a plus sign. Yep. But here's the problem. That's not the furthest thing. Because if you draw a plus that, right, see, there's a central atom, and there's your 4 areas of high electron density, and you might say, well, that's as far as they can get apart, and I know from high school that that's 90 degrees. But guess what? You're limiting it to the plane of the paper. The world doesn't limit itself to 2 dimensions. It's a 3-dimensional world. So picture that you take this prong and you take it, and you're strong chap, and you take this one and you bend it out towards you. You just grab a hold of it and you just bend it out towards you. Yep. So now that's sticking out towards you. And this one you take and you just bend it back into the page. You just take it and you just contort it and you bend it back in the page. And now you get something that 2 things are in the plane of the paper, a third one's coming out at you, and a 4th one's going back in the page. And so what I've attempted to visualize for you is this structure here. And that's called tetrahedral. Now, why does Mother Nature do that? Because you can see if you make a plus sign, it's only 90 degrees apart. But if you make a tetrahedral shape, it's 109.5. And so if you make a tetrahedral shape, it'll get these bonding these areas of high electron density farther away. And remember, that's the name of the game, to get them as far away as possible. So if this were a 4 here, you would write what? Tetrahedral. Okay. Any questions? And that's called electron. So of your electronic geometries, you've only got 3 flavors. Yep. Those are only 3 possible electronic geometries. That's it. The 3 electronic geometries. Now there's 6 molecular geometries. It could be one of these 3, or you can be variations of those, which I'll explain. But before I do that, are there any questions about counting the areas of high electron density or turning that into an electronic geometry? Yes, no? Okay. I just want to double check. Are we working out? Oh, we're doing NO3 right now. Oh, aren't you clever? Yes. Yes. Yes, you're right. Now, how am I going to move it with this one? Oh, poo. Let's see. Maybe if I, well, let me grab it. Yeah. Okay, hang on. Oh, I'm losing ground here. I'm losing ground. Thank you. Better? Is that better, Ashley? That was a good catch. Okay, right, we're doing this. Okay. So remember, your electronic geometries, if you understand what I just told you over here, hey, you got a 1 in 3 chance of guessing an electronic geometry on a test. Yep, got a 1 in 3. Okay. So now here's the next deal. Yes, just want to make, yeah, right. Well, you were absolutely right. I was on the wrong line. Okay, so let's see. I could actually clean that up a little bit, maybe. Okay, boom. That's a little nicer. Okay, right. Okay, so yeah, see y'all. She wanted to make sure it's right since I'm doing her homework for her. It says, well, if you're going to do my homework, at least do it right. Okay, so there we go. Right. Okay, so now this is, you already know how many lone pairs about the central atom. Remember, this is that about the central atom thing there. Okay, so let's see. Well, that's pretty easy because you've already drawn the Lewis dot structure. So just look at this. How many lone pairs do you see inside that circle about the central atom? The answer is 0. Yep. Oh, what if this were water? What would the answer be? How many lone pairs about the central atom? The answer there would be 2. I see 1 lone pair. I see 2. And how many areas of high electron density? So I'll give you a couple of seconds to think about that. So I'm going to do this at the side. Water. So let's work through those. So let's say you're doing water, and it says, okay, the next thing you do is you do the Lewis dot structure. The first thing you count is areas of high electron density. How many areas of high electron density for water? So the first thing you say is, okay, if I'm doing areas of high electron density, I have to only look at the central atom. So you remind yourself to only look inside the blue line. And then what are you going to count? You're going to do your 4 count thing, right? So answers, how many single bonds do you see? 2. How many double bonds? None. How many triple bonds? None. How many lone pairs? 2. So that's a total of what? 4 for water. So if we were doing water, we didn't, did we? Nope. If we were doing water, this answer would be 4. Yes? 2 from the single bonds, 2 from the lone pairs. And what would your electronic geometry be for water? It would be the only one that has 4 is tetrahedral. So water is not shaped like a boomerang. I mean, it's not flat like a pancake. Okay? It's got a shape. Water is actually shaped like a tetrahedral. Okay. At least the electronic geometry is a tetrahedral. Okay. Now, so let's continue on. So how many lone pairs about this one? 0. So where'd my... So 0. So let me put this, 0. Okay. So how do I get molecular geometry? So how does this... I told you need to know 2 now. So how does this number overlay with this? How do I combine this number with this structure to give me this answer? Glad you asked. Okay, so here's the deal. And that's where the slide over here is important. Okay, so let's look at this. To get this, and you're almost done to the end. The good news is you're almost done. You can rock and roll with these with everything except polarity. Okay, you should be able to do every one of these down here pretty quickly. And don't Google them and get the answers. I know you can do that, but you really need the points on the test, not on this report. Okay, here we go. Name of the molecular geometry. Okay, the only thing you really need to know to understand is the molecular geometry is not looking at these electrons, but it's looking at what's on the other end. So let's look at this. Let's do water would be a better, and I normally teach this with water. So let's look, I'm going to draw a tetrahedral here, and I'm going to pretend it's water. I need another worksheet here. Hang on, let me do this. Okay, so I'm going to take this tetrahedral and we're going to work with water here just for a second. Okay, not bad, not bad. Okay, here we go. So this is water, right? We agreed water is tetrahedral. Now, what I'm going to do is, and so I'm good. So now, and I looked and said, how many lone pairs are there about the central atom? And for water, we said, now we go back and say there's what? 2. So for water, that next thing would be, we had what? 4? We had 4 areas of high electron density. And if you have 4, it means you're tetrahedral. Right? 4 things is tetrahedral. And then we looked at lone pairs about the central atom, and we came up with 2. And now how does that get me to my final structure? Okay, now remember, this is electronic geometry, so we don't care about what's on the other end of these electrons. With the molecular geometry, you do. That's the whole goal, is to find out what the molecule looks like. So let's flesh this out. We had 4 things, so what was on here? Well, we had an H on the other end of one of these, right? I'm pointing to it over on the left side. And also connected to one of them was another H. And one of them was a lone pair. One of these was just a lone pair. I'll draw those in there. See that? And the other area of high electron density was just a lone pair. Does everybody see that? Can you see what I did was I now fleshed out. I treated my electronic geometry like a skeleton, and whatever was at the other end of the pair, I put it there. Whatever atom, and by the way, this central atom was what? It was an oxygen. So if I really wanted to be true, I would write a big fat oxygen there. So now, because what am I interested in with the molecules? With molecules, I'm interested in what the atoms. So here's what you need to see. Here's what you need to realize. Electronic geometry only sees electrons. It only sees area of high electron density. The molecular geometry only sees the atoms. So let me connect the atoms and see what we have here. Ready? Oh, no, I'm on a different program. Let me get this one, and I'll do that. So let me connect the atoms. See the blue? That's all I care about is the blue. That connects the atoms. Why? The molecular geometry doesn't see electrons, so guess what it doesn't see? It doesn't see any of, oh, I shouldn't do that in blue, because blue is what I do see. So what color do I not see? I don't see the orange, okay? So it doesn't see that. So what shape do I have? It looks like a boomerang, doesn't it? So the molecular geometry is like a boomerang. So we have a name for that, and it's called bent. And because that angle is 109, that's called bent 109. So let me go back and show you. Is there any questions on that so far? Okay, so let me go back and show you. So here's your only possible. There's only 6 total possibilities. Ready? Linear. Linear has got to be linear. Okay. So trigonal planar, you can have one variation. What if one of these is a lone pair? Then guess what shape you're going to get? You're going to get bent, but what's going to be your angle? 120. Okay, got it? So if you got 3 of them, you're going to have one of 2 things. You're going to have either trigonal planar, in which case there's an atom on the end of each of these 3, or if you've only got 2 atoms and one of them's a lone pair, I said I was going to do blue. If you have 2 atoms and a central atom, and this thing is a lone pair, you're not going to see it. What do you have? You're now back to your bent, but this time it's bent 120, and I've shown that out to the left. Okay, so does everybody kind of see that what's out to the left, the shape, is the trigonal planar, where only 2 of those were atoms? Yes? Okay. Tetrahedral, you can have 3 variations. What if you have an atom on the end of each one of these? In other words, you have no lone pairs and you have atoms. Guess what your shape's going to be? Well, it's tetrahedral because it didn't change. Okay? If you got a tetrahedral shape and you've got an atom at the end of every one of your high densities, then you still got a tetrahedral. Okay, here we go. But what if 3 of these are atoms, but one of these is a lone pair? I'm not removing it, I'm just hiding it, right? So what do I see here? I see a thing that looks like a triangle, but it's kind of pooched up. It's not flat in a plane like this. It actually looks like a little pyramid. And indeed, that's called Trigonal Pyramid. It's a 3-sided pyramid, right? Y'all know there's 2 types of pyramids, right? There's pyramids that have only 3 sides, and there's then the ones like over in Egypt and all of that stuff. Those with the Sphinx and all that stuff, right? Those are square pyramids. They have 4 sides. So a 3-sided pyramid. So this would be trigonal planar. Okay? And so that would be anything that you have 4 areas of high electron density, but only 3 atoms connected to the central atom. Okay, let's go back and look at your 6th and final shape. What if we have a tetrahedral and it's got 2 atoms connected to it? It's got 4 areas of high electron density. It's tetrahedral. But 2 of those are atoms and 2 of them are lone pairs. What's your shape? Bent. See the bent? It's bent. But in this case, it's bent 109, not bent 120. Okay. And guess what water is? So now you see why water. Water is bent 109.5. Why? Because let's compare what I just drew here to this. So we said water is tetrahedral because it's got 1, 2, 3, 4 areas of high electron density. So I draw myself a tetrahedral and say tetrahedral. Now say, what's the molecular geometry? Well, I know it's got 2 areas of high electron density. If I were doing water, it's got 2 areas of high electron density. And why I made you write that 2 is that's how many you're going to hide. See? If 2 of these are lone pairs, then you got to hide the 2. Because what? The molecular geometry doesn't see lone pairs. So you hide them and look at what's left. And you say, oh, it's bent. So for water, the numbers would be, you would draw the structure. It has 4 areas of high electron density. Since I'm just messing with this anyway, let's do this. Okay, you're still going to do CO2, so don't confuse yourself here, right? And you drew this. You've already done your Lewis dot structure for water over there. How many areas of high electron density? Okay, well, I'm going to circle around my central atom and count. There's 2 single bonds, that's 2. There's no double bonds, no triple bonds, and 1, 2 lone pairs for a total of 4. If I have 4, it has to be tetrahedral. How many lone pairs? How many of those 4 are lone pairs? And that's what you're asking. How many lone pairs? How many of these 4 are lone pairs? And the answer is 2 of them were. So I have a tetrahedral, and I hide 2 prongs. So that's what you got to visualize. So I've got a tetrahedral, and I'm going to hide 2 prongs. Why? Because the molecular does not see lone pairs, so I'm going to hide those. So what does it look like if I have 4 and I hide 2? I have what? A bent shape. Now, is it the bent from this framework, or is it the bent from a tetrahedral, or is it bent from Trigonal Pyramid? If it's bent from a tetrahedral, then the angles are going to be 109.5. Let's go bent 109.5. Yes? Okay. Now back to our question at hand. Now that we've done all that, nitrate had a total of 3. Remember what our symbol looked like? We had an N, and we had an O, and we had an O, and we had an O. One of those was double bond, and we had a bracket, and we had a minus on the outside. Okay, so that's what it looked like from the other page. And then when we counted the areas of high electron density, we looked about the central atom, and we did our count. How many single bonds do you see? I see 2 single bonds. How many double bonds? 1. How many triple bonds? None. How many lone pairs about the central atom? None. So my total is 3. I write a 3 there. If I have 3, what's my electronic geometry? If I have 3, my electronic geometry has to be trig planar. Of those 3, how many are lone pairs? None of them are lone pairs. They're all bonds, okay? 0. So if I have a trigonal planar and I hide nothing, what do I still have? Trigonal planar. Okay, so I would take that. And I would, boom, and there you go. Okay, so that's 2 examples that are pretty good examples right there, and that's all there is to it. Lewis dot structure, do the 4 count thing about the central atom. If the number's 2, it's linear. If the number's 3, it's always going to be trigonal planar. If the answer's 4, it's tetrahedral. That's your framework. You're then married to that. You look at how many of these were lone pairs, and it's going to be, it has, pardon me, to be less than this number. So this number has to be a 0, a 1. It's normally going to be a 0, 1, or 2. Okay, almost always. This is going to be 2, 3, or 4, and this is going to be 0, 1, or 2 for those of you doing the memorize thing. Okay, and so whatever number this is how many prongs you hide, how many arms you hide, and then you just look at what's left and tell me what you see. Okay, and that's all there is to it. That's it. So you should be able to do all of those. You should get that one right there. Yep. Okay, and you're not doing water. So as I don't get anybody barking at me, I'm going to take that off. There we go. Okay, so there's one of them. Okay, are there any questions on how to do that? Let me see, how far did I get? I don't know that this intro, did it tell you that? No, this intro only got you because this was for the pre-lab. So this intro, to be honest, only got you to the Lewis dot structure. Yes. And that's the way this lab is normally taught. So we spend some time learning how to do this, the Lewis dot structure, and then the rest of it we spend taking it from the Lewis dot structure to the molecular geometry. And then we'll learn in class, once you have this structure, how to tell whether it's polar or not. Is that actually a polar compound or not? I can tell you by looking, the answer is no. But I'll show you how you can look. When I look at water, is that polar? Absolutely, it's polar. So anyway, I'll show you how I can do that in the lab. But so because in the lecture, because the lab only goes up to molecular geometry, that's all I'm going to cover today. I'm not going to cover that last step. Okay. You might want, I think this table is somewhere in the notes. Feel free to write these down. You should do it so much you have them memorized. So, in summary, you've got a formula that you can do. Yep, almost done. So you're going to take, I'm going to give you a formula. And you're going to do the NASA table in a Lewis dot structure. And you're going to look for these two tripwires every time you're going to train yourself. Because, see, you're going to see it in here. There's an ion, and I see some smaller than carbons. So there's going to be exceptions bedded all the way down there. So make sure you do that. And then once you get your Lewis dot structure, you're going to do what? Once you get your Lewis dot structure, you're going to count areas of high electron density. And you're going to write that number there. And then once you do that, you're going to tell me what the electronic geometry is. Linear, trigonal planar, or tetrahedral are your only three choices. You're going to write that word there. And then once you do that, you're going to say, of those, of the number here, how many of those were lone pairs? And you're going to write it there. And then whatever number is there, you're going to hide that many prongs on your electronic geometry. And whatever's left is your molecular geometry. And there's the number of lone pairs, and there's that. And you're done. Okay. Can y'all do it? Any questions whatsoever? Okay, can you work out the NASA table for one, such as the first problem that has 3 elements? What would you subtract to give the bonding pairs? I won't work that one, but let's see if I can find another one that's kind of similar to that. Let's see. Oh, this is, hang on. Okay, let's see if I could think of one with 3. One with 3 elements. Can you work out an S-bar for one? The first that has 3 elements. Would you subtract? Okay, so I could think of one, but it's going to look very much like nitrate. But let's see if I can. What could be one that I could do here? Right. Let's see. Let me do my text right quick. Right, let's see. Well, that's kind of wanky there. Let's see. Okay. Okay. I could do Cl2. Let's see, SO, there we go. Okay, so let's just kind of work through something. Whether this compound even exists, I don't know, but we're going to work through it. Okay, so we'll just go through one fast motion. Ashton, are we meeting tomorrow? Are meeting tomorrow for what? Okay, let's see. Right, so the first thing you're going to want to do is pick out your central atom, and I'm guessing S, those, okay, so or if you're not sure on a test, sometimes I'll spot you, I will tell you what the central atom is, just like I did for this worksheet here at the bottom. Okay, so we're going to do S, and then O, and then, ooh, this mouse is bad, and then Cl, and then Cl. Okay, so let's see. So there's that. So let's begin doing our NASA table. I have 2 Cls, and am I using that one? Oh, shoot. I'm using the wrong one. Okay. So I'll go back and do that in a minute. Okay. So I have 2 Cls, right? And I have 1 sulfur. Let me see. Are we meeting tomorrow? I don't know if you're asking, but yeah, if you're asking if we have lecture class, yeah. If you're asking if we have lab, yeah. 1s plus. We're just, it's the way the semester's shaking out. We're just going back to normal timing. Okay, so there we go. Okay, so let's look at this. Let's try to get this back on. Okay, so each of my chlorines, let's do the needs line, okay? Each of my chlorines needs 8, and each of my sulfurs need 8, and each of my oxygens needs 8. So there weren't any exceptions on that. Okay, for a total of, what do we got? 4 times 8, if I'm doing that right, 32. Okay, how about available? Each of my chlorines, and they're in group 7, they're in group 17. So they're going to bring 7 to the party. And my sulfur is going to bring, it's in group 16, so it's going to bring 6 valence electrons. And my 1 oxygen, as usual, is going to bring 6 electrons, same as every time. So that's for a total of 14 and 12. Can I do that in my head? 26. Let me know if I do the math wrong. Okay, so how many shared electrons are we going to have? 32 minus 26 is equal to 6. Does that seem right? Okay, so what do I have? So 6 means I'm going to have 3 bonding pairs. Really? Is that right? That doesn't seem right to me. Oh no, I think I gave you up. Let's see, I think I screwed up. I pulled one out of the head, which might have been a general chemistry one. Let's see. 60, yeah, 832. Chlorine is 7, yeah. Sulfur is 6, 12, and 14. It's 26. 7, 2, 8, 9. Oh, shoot. Okay, well, I'm going to go ahead and do this anyway. Okay, and so how many were left over? Okay, I'm still going to have to do this. So 26, so that's going to be what? 26 minus 6 is equal to 20. And so there I have 10 lone pairs. Okay, well, this isn't going to be exactly right, but okay, we're going to go with this at any rate. Cl. Okay, so we've got that. So what do? We now have to flesh this out. We got 3 bonding pairs. I see 3 bonding pairs. I need 10 lone pairs. What's the rule we use here? Outside in, right? So let's kind of do that. Since I wrote small, I guess I want to do this. So we know we'll start fleshing these out. How many does chlorine need? 8. So let's do 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Stop. Everything on the outside is like it should be. Yes? So each of my chlorines has 8. And my oxygen has 8. So how many bonding pairs have I used? 1, 2, 3, 4, 5, 6, 7, 8, 9. How many am I supposed to place? 10. So what does that mean? 1 now goes here. Right? Get the outside done. Anything that's left, you have to do the inside. Throw it on the inside. So now you can see I have 10 lone pairs. So let's now go to this different color. And let's now go about the central atom. And let's do our 4 count thing. Ready? Okay. So now we've got this. So the first thing I want to know is what? The numbers of high electron density. And what is that? I do the 4 count thing. Ready? How many single bonds do I see? How many double bonds? None. How many triple bonds? None. How many lone pairs? 1. So what's my total? 4 areas of high electron density. So what's my shape? Only one with 4. If it's 4, it's tetrahedral. It looks like that. I'm going to write that in my answer sheet. Okay? Ready. So now I need to do that. That's my electronic geometry. It's tetrahedral. Now I need to go to my molecular geometry. So what do I ask myself? Of this 4, how many of them were lone pairs? And the answer was 1. So what does that mean? I have to take this shape. 3 of them I have to put atoms on the end of it. And 1 of them I'm going to scratch out. Okay. Now remember, I'm not removing it or it'll change the shape. So here's what I need to visualize in my mind's eye. 3 of these. This one has a chlorine, this one has a chlorine, this one has an oxygen. And if I wanted, I could actually, instead of drawing a dot on a test, I would probably do this. I'd put a chlorine on one, a chlorine on one, a chlorine on one. And I wouldn't change my shape. I would just remember that I'm going to pretend I don't see that one. Yep. Now remember, it's still there. You're not going to go trigonal planar because it's 3. Once you have a tetrahedral framework, you can't change that. Okay? So I'm going to hide that one because there's nothing on the end of it. And what do I see? I see the 3 things. So I actually see, if I turn it on its side, I see what? Trigonal pyramid. See the pyramid? It's turned on its side. There's the pyramid turned on its side. Okay. But I know that anyway. I've memorized it. I know that you take a tetrahedral and you take one thing off and you got what? Trigonal planar. Okay, so that then goes to, I would write trig without a mouse. Planar. No, oh, trig pyramid. That's why if you just write trig, it's going to be counted wrong. Why? Because there's 2 flavors of trig. Trig planar and trig pyramid. So trig does not get you half point. The word trig gets you nothing. Because I don't know that you know what you're doing if you do that. Okay. Also, the word bent doesn't get you anywhere because there's 2 bents. And I know you know it's bent, but I know you won't know what this number is unless I know you understand the concept. And that's why. So you could abbreviate tetrahedral, T-E-T-R-A. I'm good with that. You can write linear. You could call that trig planar. That's fine. Trig pyramid. You can abbreviate trigonal, trig if you want. Fine. But you can abbreviate it trig, but I want to see something else. Trig by itself or bent by itself doesn't count for much. Matter of fact, it counts for nothing. Okay, so that was kind of fast paced, and you'll get to where you guys can all go through them that fast. They're really just, there's a lot of moving parts, but if you practice about 10 or 15 or 1,000 of them or whatever it takes, then you'll see that they're all just kind of the same. But this lab is really good practice. It's really, really good practice for the exam, because that's exactly what you're going to have to do. Okay, did that answer your question, Ashley? Yes, got it. Yeah, good. It's really not that hard. It's very simple, but there's a lot of moving parts. You know, it's my watch analogy. I mean, what is a watch? All it is springs and gears. That's all it is. How hard could it be? Well, it's hard to put them all together to make it work, even though the parts are very, very simple. It's integrating it all together that's kind of tough. So when I say this is simple, I mean any one of these steps is really, really simple. I could teach it to somebody in junior high. The problem is pulling it all together, you know, putting all the gears and sprockets together so that it actually tells time. Well, that's a different story. So don't get overwhelmed by looking at it all. Just make sure you can do each of those steps of the cascade. You just want to think about it as 6 really, really simple steps, and not one really big, huge jumble step. And each step, go really slowly and say, okay, look for the tripwires. In every step, I've told you what you need to look for. What's your tripwire here? You don't look about the central atom. You count them for the molecule. What's your tripwire here? You look for smaller than carbon, but you forget to look for ions. What's your tripwire on this second step? Oh my gosh, I didn't pick the least electronegative as the central atom. Or I picked hydrogen as the central atom. Either one of those are wrong. What's your tripwire here? Again, you either forget the central atom or you forgot to just hide the lone pair. You actually removed it so that it was supposed to be tetrahedral with one prong hidden, but you actually removed the prong, and so you now think it's trigonal planar because you've only got 3 things. No, it's trigonal pyramid because you're only hiding the lone pairs. You're not actually plucking it off there. And that's the end of the lab. So, kind of in summary, you should be able to go from a formula all the way down to a molecular geometry, and you might want to refer back until it gets solidified in your brain, each of the steps that you need to go through and each of the warnings or tripwires that you need to pay attention to as you move from one step to the other.